just asking you, have you guys gone through that chapter 5? You know, we went through 3 types of spring mass system, that is without damping, then free damped motion, and then the driven force. These 3, and then after we went over the LCR circuits, and immediately I posted that one on YouTube too. But it looks that you guys have not gone through it. Please guys, every day we are spending some time for the review session so that it will be helpful to you for your next test. That's the reason. So please guys, please. Last test will be the combination of chapter 5, chapter 8 and chapter 9, chapter 7. I told you this thing, so please be careful. We finished chapter 5 when I gave some of the examples in homework. Almost I solved all the examples. Only a couple examples are there in homework. So please go through it, please. It is the usual practice, or I would say that if you go through the same classwork on same day, that means you are reducing your efforts preparing yourself for the exam, because already we are going through the stuffs over here in class, and then after, if you try to solve the same things, if you try to go over the same things on the same day, that means because everything is really fresh for you, and that's why you can catch that thing, you can grasp that thing very easily. So that's the reason I'm just forcing you to go through all the stuffs. Somehow, suppose you are missing some of the things, you can again go through the videos and like this on YouTube, so you can't miss anything. Suppose you want to look at the solutions of some of your homework assignments, again you can go through the YouTube and try to look at the things, try to understand the problem thoroughly, because if you look at the cursor on YouTube, again it is exactly same as the class notes, classwork. So please do this thing guys, please. Anyway, just 1 week, I would say, not more than 1 week, because probably I will be done in a week. So then after, the ball will be in your court, so you need to work hard to go through all the stuff, and the final is cumulative. So please keep in mind this thing, final is cumulative. So yeah, starting from the beginning, chapter 1, 2, 3, 4, 5, 8, 7, everything will be there in the syllabus, right? So please be careful guys. Okay, and now let's start chapter number 8. So let me share my screen. Oh, sorry, I'm sorry. Where is my class notes? Is it here? No. Where is the class notes? No, it's not here. It's not here. So all windows. Just now I opened the class notes. Why it's not here? Okay, let me open that one again. Class notes and okay. Why I'm not getting the class notes? What's the reason? Yes, here. Okay guys, so that's what we did yesterday. Look at over here. This is the LCR circuit, and I told you that whenever you have a capacitor in the circuit at that time, most likely your differential equation will be a second order, because you cannot work with two dependent variables I and Q. You have to convert either in terms of I or in terms of Q, and you know that this relationship I equal to dQ over dt. dQ over dt. So if you plug this value over here, either you convert your equation in terms of the current or the coulomb, you're going to get the second order differential equation because of the presence of the capacitor. And you know this thing, that capacitor was not there in chapter 3, right? And if it was there, but we converted that one in terms of some other, I mean to say, current. So So please keep in mind this thing and make sure that whenever you have a damping force like this, at that time you have to mention separately which type of damping you are working with. Either it is under damping, over damping, right, or critical damping, whatever it may be. So please do this thing, guys. Don't lose your points because of your idleness. Please don't be don't be lazy and try to go through everything the way I'm writing over here. Please write in the same way. If you want to look at the Paul Mustain's work, I really appreciate the way he's writing. That's really, really good. And second one is Margie. Margie's exams are good. But if you look at the Paul's work, his homework and exams, both are good. So please try to follow. If he allows you to look at his exams or like this, I don't mind, but you need to take his permission. So that also you can come to know that how to write the exam so that you can lose minimum of your points. So please try to minimize the things for your teacher to cut your points. I don't want to cut your points. You know this thing. I'm always in favor of you. Sometimes I become strict, but that is for you guys. That is for your betterment. I told you very first day that if you are going to clear this course with A grade, I'm not going to gain anything. And if you're going to fail this course, I will not be the loser. But please, guys, be sincere. That is equally important in the life too. If you are sincere, not just particularly for my course, but if you are sincere in all your works, that will pay you a lot in your future. Trust me, guys. Trust me. That's my own experience too. Anyway, that's okay, fine. Still, you have lots of time. You are the future of this country. So if you are good, most likely our country will be good, right? So please keep all these things in mind. Be a good citizen and hard worker. Try to make a good career and live a good life, right, guys? Anyway, so that's the different thing. Yeah, let me continue with this one. Yeah, first, second time, third time, I give instructions in a very mild form. But if I find that you guys are not following my instruction, then of course, I'm getting upset. So don't try to upset me, guys. If you are following me, our atmosphere will be very, very healthy and you are going to learn lots of things from me. Yeah, and we can discuss lots of things too. But in that case, you need to just follow my instruction. You need to work hard. And that is just for your betterment, right? You're not working for me. You are working for yourself, guys. So please be careful. Okay, so now we are going to start the new chapter, that is the system of linear first order differential equation. System of linear first order differential equation. You can see over here, my title says that system of linear equations, linear first order differential equations, right? That means we are not working just with one differential equation, but we are working with the series of equations. Yes. One more thing, if you use MATLAB or Mathematica, there is a software that is called DFQ, differential equations, partial differential equations. There are some tools. If you use those tools, you are going to get, and if you install, if you put all these equations in your DFQ tool in MATLAB, you will be getting solutions directly. Unfortunately, we are not allowed to use this MATLAB or this type of software over here. Yeah, but otherwise you will not come to know how this method works. So that's the reason. First of all, we are going to learn these things manually, and then after, in your numerical analysis of differential equation and partial differential equations, most likely that will be the another course for you guys, whether you are at VMI or outside VMI. That will be the another course. So if you go through that course, you will realize this thing, that how technology works fastly, very fast to get the solution. But at the initial stage, you must know how to get the solution manually like this. Whenever we have a system of equation, at least that means we are converting those equations in terms of the matrix. Once we have a matrix, that means again, in method of partial fraction in Calc 2, I don't know how your teacher taught you, but probably Ismail Taylor, he knows this thing, because in method of partial fraction, we take help from the calculator and we use RREF, reduced row echelon form. Because we converted in method of partial, we converted our algebraic equations, of course, in terms of some matrix form. Here, instead of algebraic equations, we are converting our differential equations in terms of the matrix form. So again, the theme is same. We are going to take the calculator, I-84, 83, 84, 89, whatever you are using, I don't mind. All of them, they are having the same tools. So you can use RREF command and try to get the solution of the system of equations, I would say mainly for the unknowns. Look at over here, these are my unknowns, x1, x2 up to xn, right? Try to get the solution using the technology. But the best way I mean to say that in future, suppose you are working in some field, in some form where you require to solve a series of equations, differential equations, at that time, nobody is going to ask you how you are getting the solution. But right now, of course, this is the demand of the course that we need to go through the solution using matrices manually. But whenever after a few years you will be doing some job in some research firm or any of the firms, at that time, suppose you are required to solve the differential equations or partial differential equations, series of equations, I would say, at that time you are not required to solve all these things manually. Just use your package, I mean to say your technology, software, MATLAB, Mathematica like this, and incorporate all your equations. Just enter it and you will get the answers with your figure also, right? So technology really works good sometimes, not always. Yeah. Okay, guys. So that's the things. And at that time, you have to be very precise about your domain and everything. So once you know to solve the equations or system of equations manually, it would be really very easier for you to use the technology. People are using sometimes, not always, but people are using technology without making any sense, without knowing the theoretical portion. And that's the biggest drawback nowadays in our research field too. I'm not talking about just your course, just the elementary level course, undergraduate or graduate level course. I'm talking about our research tools too. Very few people in the world, they have a knowledge of pure and applied mathematics both. I don't know why, but people just bifurcated mathematics into two parts. One is pure and one is applied. For me, I think they are just two sides of one coin. If you don't have two sides, that means that coin doesn't have any value, right? You have to have two sides well defined to have proper value of the coin. It's exactly like this. But sometimes people say that I'm an applied guy. I'm a pure guy. I think that's a drawback from our side. Yes, from our side, from the research community, that's a drawback. You should not think like that. If you claim that you are a mathematician, that means you have to have the maximum knowledge, and that never ends. That never ends. And that is same in your field too. Knowledge never ends. If you think that, yeah, I'm just giving you some advice, probably helpful to you in your life. If you want to follow me, if you trust me, yeah. Trust is the best thing to follow somebody's advice. If you don't trust me, you are not going to follow me. Yeah, that's the mentality. That's the human nature. Yeah, so if you are sincere, what I was talking about, what I just forgot. Yeah, so yeah, just try to be matured and develop a habit that every after 3 days or every after a week, you are going to learn something new, something new. Right now, you are learning lots of new things daily, but I'm not talking about just your syllabus. I'm talking about anything. Suppose somebody doesn't know any kind of spirituality. Okay, go ahead. Read some book, read Bible, whatever you want, whatever is your religion, whatever your religion is. Just try to spend 15, 20 minutes a day. Fine, learn some new things. That's good. If suppose somebody is really enjoying some sports, okay, go ahead. Try to look at the biography of some good character in that field. Do this. Please, I mean to say that please develop a habit to learn something new, something new. That will make a big difference in your own character. Whatever you are right now, after 5 years, with this habit, after 5 years, your characteristics will be completely different. You will be identified separately in a group of 100 people, because now your thinking ability is different. Your attitude is different. Way of thinking is different. So you will be identified, and that is what corporate sector requires. Yeah, they just don't want only your knowledge. No, once you are graduated, that means everyone is just same. It's a matter of some plus minus. But then after, your attitude matters, your behavior matters, your skills matters. Different skills. How to convince the people, how to behave nicely, how to work in a group, all these things do matter a lot. So anyway, guys, that is just the future. But main thing is, if you are confident, you will be confident once you have some knowledge. If you are working on this chapter, suppose couple hours a day, after 4 days, you will be confident. Why? Because you worked on it. Because now you got the knowledge of this one. So that's why hardworking. I told you so many times that there is no any kind of option or alternative for the hard work. Do it, guys, and respect everyone. Yeah, whether somebody is elder than you, somebody is younger than you, that's fine. Respect everyone. Okay, guys. Good. So now, suppose, let me start nth differential equation. Of course, you can see over here, first order, first degree differential equation. You can see here x1 power 1, x2 power 1. They are separated by plus sign. That means all my dependent variables, see, dependent variable and all its derivatives, they are of first degree. You can see over here, the degrees are 1 everywhere, and they are not multiplied together. So it is a linear differential equation. That's what definition says according to your first chapter and fourth chapter, right? So that's the linear differential equation. So they are not multiplied together. They are of first degree and are not multiplied together. This is my right hand side f1t, that is non-zero function, dx1 by dt derivative. Okay, here A11, that is, I would say that A11 stands for, first one stands for your row, second number stands for your column. So I would say first row, first column. So first row means this row, first column means this column. That means whenever I say A11, that means I'm talking about this number. Whenever I have same numbers, A11, A22, that means I have A11, A22, A33, A44, A and N. That means I'm talking about the diagonal elements. If I say A12 means first row, again the same row, and first row and second column. So whenever your rows and column, the row and column are intersecting, at that time, that is the element we are talking about. So A12, like A1n, first row, nth column. Then A21, so you can see here, my 1 is fixed everywhere because we are just talking about the first row. So first position is fixed. Second position is fixed, A22, A2, 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 A2. But here is 1, 2, 3 up to n. Then after A31, so third position is fixed, A31, A32, A33, and A3n, like this. But if you look at the column, A11, now my column is fixed. First column, look at my last number, 1, 1, 1, up to 1. So my column is fixed. My column is fixed and rows are different. See, first row, second row, third row, like this. So that's how we can write. This is nothing but the coefficient matrix. Once I have n by n matrix, here I have taken some n rows. Look at over here, A11, x1, x2 up to xn, right? x1, x2 up to xn. And here also, first column, second column, up to first column, A11, first column, second column, and then up to A1 and A2 and nth column. That means last element is A and n. I mean to say that nth row and nth column. nth row and nth column. So please do this thing, guys. So n equations with n unknowns. This x1, x2, x3 are unknowns. Whenever we have a system of equations like this, we can always write this system of equation in this form. My left-hand side is dx1 by dt, dx2 by dt, dxn by dt. So I can write d by dt out and x1, x2, x3 like this. Or you can write x1 dot, x2 dot, xn dot like this, that just represent the derivatives. And these are the coefficients of the matrix A11, A12 up to A1 and A21, A22, A2n. So that is a coefficients of x1, x2, xn like this. And unknowns x1, x2, this is the coefficient matrix. This is called the matrix of unknown. You know matrix multiplication. Am I right, guys? How many of you don't know matrix multiplication? Will you please let me know?
I don't, sir.
You don't? Are you sure, Ilyas?
I may have seen it before years ago, but I don't remember how to do it.
Oh my gosh.
Neither
Yeah,
do I, sir.
I can look it up online, sir, after the class.
No, that's fine. Any other guy who doesn't know?
I don't believe I got it.
Who is there? Alex?
Alex.
Okay, let me spend some time with you guys. I hope other guys, they don't mind, right? Guys, please cooperate them. Okay, so let me stop sharing this one and let me start my screen. Sorry, whiteboard. Where is it? So let me stop this one and let me share my whiteboard. Look at over here, guys. Suppose I have one matrix like this, whose elements are 1, 2, 3, then 4, 5, and 6, and 7, 8, and 9. 7, 8, and 9. And my another matrix is like this. Suppose I have suppose let me write like this is 3 by 3 matrix. 3 by 3 matrix. And suppose I have 1, 2, 3, 4, 5, and 6 like this. First of all, please make sure that matrix multiplication that is possible only if the number of columns of first matrix that must be same as number of rows. Let me write like this: 1, 2, 3, and 4, 5, 6 like this. Yes, this is better. So that is same as number of. Can I erase this part? Where is my eraser? Here. Let me erase this one. Let me erase this one. Let me erase this one. Okay. So let me write like this: 1, 2, 3, 4, 5, and 6. 5 and 6. And you can see first, second, and third. So 3 rows and 2 columns, right? So whenever the number of columns of first matrix that is same as number of rows of second matrix, in that case, matrix multiplication is possible. So matrix multiplication is possible. Otherwise, it is not possible, right? This is the necessary condition for the multiplication of two matrices. Now, whenever we are looking for the multiplication at that time, please make sure that this is my first row. This first row is to be multiplied with the first column corresponding elements. Means 1 is multiplied with 1. So I would say that 1 is multiplied with 1 is 1. Then 2 is multiplied with 2. So that is equal to 4. And then 3 is multiplied by 5. That is equal to 15. So that will provide me the first element of my product of matrix. Then after, you are not allowed to change your row. Just stay with the same row and then go for the another column. So this is my second column. So my second column will be 1 is multiplied, again the first element, this 1 is multiplied with 3, then 2 is multiplied with 4, then 3 is multiplied with 6, and plus sign in between. That means I can write over here 1 3s are 3, plus 4 2s are 8, plus 6 3s are 18, and my bracket complete. Then after, I can start the same thing with the second row. My second row says like this. Here it is 4, 5, and 6. Again, let me start with first column and second column. So 4 multiplied with 1 is 4. And then after 5 multiplied by 2 is 10. And 6 multiplied by 5 is 30. And here it is, you can see 4 multiplied by 3 is 12. 5 4s are 20 and 6 6 are 36. And then after, let's go for the third row. Third row is this one, again 2 columns, 1 by 1. 7 ones are, 7 ones are 7, and then 8 2s are 16, and then 9 5s are 45. And then after, you can come over here. So 7 3s are 21, plus 8 4s are 32, and plus 9 6 are 54. If you just add these numbers, you are going to get like this: 15 plus 5, that is equal to 20. So that is my first number. Then 18 plus 11, that is equal to 29. Then after, 30 and 10, 40 and 34. Then here it is 36 plus 20, that is 56, plus 12, that is equal to 68. And then after, you can see over here 45 plus 7, that is equal to 52, and 52 plus 16, that is equal to 68. Am I right, guys? Sorry. Yeah, that is equal to 68. And then after, you can see over here 54 multiplied by 32. So 54, 5, 6 and 7 is here, and then after 5 and 6, 7 and 8, 9 and 10. So it is 107 like this. What is the size of this matrix? That is again 3 rows, and you can see 2 columns. So size of the matrix will be like this. Always size of the matrix will be your first matrix row multiplied by second matrix column. That would be the size of the matrix, and that's what we are getting over here. Look at here. So that's how you can go for matrix multiplication. Any doubt?
Yes, sir.
No, sir, that makes sense.
Probably the
Alright.
reason for you guys, right? Okay, so that's how one can multiply the matrices. One can multiply the matrices. So let me stop sharing this thing. And now again, I would like to go to my file. So let me stop this one. And let me again share my file here. So that's how. Now you can see over here, as I told you, my first row, fixed row, and try to multiply corresponding elements. Here just one column is there. Here it is n by n matrix, and here it is how many rows? 1, 2, 3 up to n rows and 1 column. So n by 1. Because number of columns for this matrix is same as number of rows over here, that means product is quite possible. That means I can multiply a11 with x1, a12 with x2, a1n with xn. So a in between plus sign. a11 x1, that means my first element. a12 x2, that is my second element. a1n xn, that is my third element. Plus f1t, that is this one. And here it is d by dt of x1 or x1 dot. That means I'm writing my first equation. So that's the way, or that is the main reason to convert the matrix, equations in the matrix form, right? Now, this is my x dot. This left-hand side is my x dot. This is the coefficient matrix I would like to denote by capital A. That's the general universally accepted symbol. And this is my capital X. And this is my some capital F or B, whatever you want to say. So look at here, guys. Look at here. So this x dot is nothing but x dot means my, now if I say that x dot, that means just please keep in mind this thing that I'm talking not about just one variable, I'm talking about the matrix. If I say A coefficient matrix, I'm talking about this type of matrix. If I say capital X, that means I'm talking about the matrix of unknown. So just by finding X, we are not finding just one variable, we are finding all these 1x, 1x, 2x, and all n variables at 9. And F is my right hand side. Some people write D over here, some people write X, that's fine, that's called the non-homogeneous term over here because right hand side is non-zero. Right? As per example, let me give you a very simple example of 2 by 2 matrix. dx by dt equal to 3x plus 4y, dy by dt equal to 5 minus or 5x minus 7y. So if you take the coefficient, so 3, 4, 5, negative 7, that is my coefficient matrix. X and y, that is this one. If you multiply this with this one, you're going to get back your matrix, your system of equations, 2 equations. And here d by dt is x and y, so x dot and y dot. So I can write x dot equal to ax form, and there is no non-homogeneous portion over here. Right hand side is 0, so I would say 0 matrix. Don't say simple 0. Now it is 0 matrix. 0 matrix means all the elements 0 inside the matrix. 2 by 2 matrix, that means here you have matrix with 0, 0, 0, and 0. those two columns, 0, 0, 0, 0 entries. Alex, are you okay?
Yes, sir.
Okay.
That's all my notes.
Okay, fine. Now, I told you so many times that I like this book, ZIL, that is ZIL, Elementary Differential Equation, then X and Y. Because look at over here, he maintained the continuity. And that's the reason I just dropped chapter 7 and I just jumped to chapter 8 after finishing our chapter 5. Our chapter 1 started with the introduction portion. Chapter 4.1, article 4.1, again the introduction portion for higher order differential equation. This is the introduction for the system of equations. I am not solving any kind of system of equations right now, but right now I'm just providing you the general informations about the, or I would say the introduction for the system of equation. So solution vector on I is any. Now solution vector means X. So what do we mean by this solution vector? This solution vector is nothing but, as I told you, that is all your vectors x1, x2 up to xn. So this solution is the column matrix x1, x2, whose vectors are x1, x2 and xn. All these are the vectors whose entries are differentiable functions, right? Because these all must be, you must get the derivative of all these functions. It should be differentiable functions, right? And that's why we are taking x dot over here. Look at here. So whose entries are differentiable functions satisfying this condition, Ax equal to f. That means if you take the derivative of your solution, you must get your left-hand side. And if you plug this values of x over x1, x2, xn, all n vectors over here, that means you are getting your right-hand side. And equality must be satisfied, means left-hand side must be equal to right-hand side. Left-hand side must be equal to right-hand side. So that is the solution operator, solution vector. Whenever you are writing the solution vector, make sure just like your differential equation of first degree, first order, or you can say for higher order, that it should be free from radical of fractions, or it should be free from your derivative terms too, right? So solution doesn't include any derivative. That's why it is called the solution. Okay. Now, I told you that we are going to use this one as a formula set. I told you, I put this one in our practice test assignment too. And I told you to take the printout of this thing because you are using this one in your last test, as well as you are using this one in your final. So please take the printout of this one. Now, once you have a matrix form of the system of equations, that means this matrix A, let me go back, this matrix A plays a big role. Big role, I mean to say that the solution is obtained using the eigenvalues and eigenvectors. So eigenvalues can be found using this A, eigenvectors can be found using this A. So this unknown matrix or coefficient matrix, I mean to say, I'm sorry, coefficient matrix makes plays a big role. Matrix that is obtained by the equation absolute value, or I would say determinant A minus lambda I equal to 0. Absolute value or determinant of A minus capital A is this one, minus lambda is the eigenvalue corresponding to eigenvalue, of course, and I is the identity matrix equal to 0. And then find the value of lambda. And that value or values of lambda that will provide you different roots. Depending on the nature of this lambda, I say that it could be real and distinct. It could be real and same. It could be complex. For our study, I would like to restrict to just two roots. One is real and distinct. Second one is real and same. And that is the big thing. Again, guys, look at here. Article 4.3, we introduced different 4 kinds of roots. Roots are real and distinct, real and repeated, complex conjugate, and repeated complex conjugates. Exactly same theme we are following over here now. See here, the introduction portion is there. That means the author follows exactly the same theme, whatever he has introduced in chapter 1 as well as chapter 4, right? And that's the best way of writing the book. Okay, guys. So whenever your roots are eigenvalues, I mean to say roots are real and distinct, It is quite simple because now look at over here again, my x1 is this one, x1, x2, xn. I am talking about capital X, but capital X contains my vectors x1, x2 up to xn. So my x1, just one vector can be identified as k1 e to the power lambda 1t because lambda 1 is one of the roots. Lambda 2 is another root. Lambda 3 is another root. But now you have to multiply by some constant, just like your chapter article 4.3 c1 e to the power lambda x plus c2 e to the power lambda 1x and lambda, right? c1 e to the power mx plus c2 or m1x plus c2 e to the power m2x. That's what we went through in chapter 4. Here it is lambda because now lambda gives you some real numbers, some numbers. So if lambdas are different and real, so k1 e to the power lambda 1t, k2 e to the power lambda 2t, k3 e to the power lambda t3, kn e to the power lambda and t is your dependent variable, just like your chapter 4. It's exactly same. So right now, let me just go through this one whenever your roots are real and distinct. I don't want to discuss the roots are real and repeated right now. I don't want to confuse you at the same time. When the time will come in article 8.2, I will let you know this thing. So let me skip this part right now. It's a formula set again, right? Because whenever roots are real and repeated at that time, we have to take care of some different numbers, m and n, but I will let you know when the time will come. Excuse me, when the time will come. Okay. So now let's start the verification. If you remember, we went over the verification of first order, first degree differential equation when one differential solution was given to you and we just verified whether the given solution is actually a solution of the given differential equation or not. That's what we meant by verification, and we did the same thing in our chapter 4 also. Am I right, guys? Verification. Now again the same theme. See, we are following exactly on the same base, same theme. Verification verified that this x1 1 and negative 1 e to the power negative 2t. This is your k1 e to the power lambda 1t. Lambda 1 is negative 2. x2 k2 e to the power lambda 2t. So these x1 and x2 are solution or solution vectors of the system of equations, system of two equations, x dot equal to 1, 3, 5, 3 and x. That's what we need to verify, whether these solutions or not. I have not given you the technique how to solve this system of equations, these two equations, and get this one, these two as the solutions. I have not given you this technique right now. Just accept this one, but I just want you to check this condition, check this thing, whether these two are the solutions of this one or not. Okay, I told you the definition of the solution says that whatever x1, x2 you are getting, they must be a differentiable vectors, right? So let me take the derivative of this x1, derivative of this x2. Before that, let me multiply this one, let me multiply e to the power negative 2 with my matrix, right? So I'm getting this one. And that's why I change the color. Look at this, here is the blue color, then it is black color. So you are provided only this part. I wrote it down as a solution or as a verification. I wrote it down in a simplified form, compact form. Same here. If I want to verify this one, that means it has to satisfy my differential equation star, previous page. That means x1 dash must be a times x1. There is no right hand side, means no non-homogeneous term, homogeneous terms. The equation is there. So verification, I mean that I want to verify this one, x1 dash equal to ax1, x2 dash equal to ax2. x1 dash equal to ax1, x2 dash equal to ax2. So first of all, let me take the derivative of this one. So this capital X stands for matrix form. Capital X dash means x1 dash and x2 dash. x1 dash and x2 dash. This matrix as it is. And here it is x1, x2. I told you all these capital symbols, they are nothing but your vectors or matrix. All are the matrices. Okay. Now you can see over here. So x1 dash and x2 dash. So let me first try to solve my left hand side. My left hand side x1 dash, let me take the derivative of my first operator, I mean the first vector. So x1 dash is negative 2 e to the power negative 2t, and here it is plus 2 e to the power negative 2t. That is this one. x2 dash, that is equal to, and that's why I multiplied here. So 18 e to the power 60 and 30 e to the power 60. That's what I'm getting over here. This is my x1 dash and x2 dash. So I found these two parts, my left-hand side. Now I'm going to take my right-hand side to verify this thing. So my right-hand side is x1 means x1 as it is. And A matrix is the coefficient matrix. I'm getting 1, 3, 5, and 3. 1, 3, 5, and 3. So 1, 3, 5, 3. 1, 3, 5, 3. That is my A matrix, AX1. So this matrix, coefficient matrix, is multiplied by this solution. Here, this is 2 by 2. This is 2 by 1. Number of columns over here, a number of columns in first matrix that is equal to number of rows in second matrix. That means this multiplication is quite possible. If you multiply this one, you're going to get this one. Negative 2 e to the power negative 2t and 2 e to the power negative 2t. You can see over here, this one is exactly same as this one. That's why I put this line. Look at this light, not dark, but light line. So you can look at over here, guys. This x1 dash is same as this one. That means it is verified. That means it is verified. Same here for x2 dash. So x2 dash, already you figured it out, your x2 dash. Now I want ax2. So my coefficient matrix is multiplied by the second solution, second vector. So if you do this thing, you're going to get ax2 also. So that's what I mean by the verification. I did ax2 over here. Any doubt, guys? Any doubt here? And that's why I wrote it down, verified, right? That's why it is verified. Okay, guys. And then after, let's go for initial value problem. Again, see, now verification, after verification of system of equation is nothing but just your number of equations, differential equations. That means it is very natural that we can incorporate some initial conditions with each of these equations. And that means I can incorporate my first condition, x at t0 equal to x1 at t0, x2 at t0, xn at t0, like this. These are the initial conditions corresponding to each of those equations and equations, right? Where x0 is x1, x2 up to xn. x0 is nothing but x1, x2 up to xn. I'm sorry. Yeah, x1, x2 up to xn, right? So whenever your system of equation, again, my capital X dash, that is not just one difference, that is the number of x1, x2, x3 up to xn dash is there. Same here. So it's a system of equation or matrix form, matrix equation, and here it is matrix initial condition. Initial condition in the matrix form, number of initial conditions, number of vectors are there, x1, x2 up to xn at same point t0, same, that's why it is called the initial condition. I told you when you have to have this t0 and this t0 same throughout, that's why it is called initial condition. If it is different, here it is t1 and here it is t0, it is called the boundary condition, but we don't want to go through this one. So in that case, this is called the matrix initial condition or system of differential equation with initial condition, that is called the initial value problem for the system of equations. Initial value problem for the system of equations. And then after, I would like to go for the superposition principle. Superposition principle, that means each of your solutions are multiplied by some constants, different constants, C1, C2, C3 up to Cn. And then we are taking the addition of this one. That means it is a linear combination. Look at over here, all the solutions. See, I told you in chapter 4 that suppose you have second order differential equation, that means it has two solutions. But if you take the linear combination, those two solutions are multiplied by some two different constants, C1 and C2, and in between plus sign, that is called the linear combination. Linear combination is the another solution of the same differential equation. Exactly same over here, that the linear combination C1, x1, C2, x1, x2, xn, they are the solutions. Solution vectors, I would say. So if you multiply all your vectors by different constants C1, C2, Cn, that means they are nothing but the linear combinations. Linear combination is the another solution of the given system of differential equations. Please try to pick up my words every time, please. Otherwise, you will be getting confused. If you miss some of the part and if you forget to ask me, that sounds good to me. No problem. Just go through my YouTube videos and refer that one. You will realize this thing very clearly. Now, one more thing. Once I say that, it's a linear combination. Linear combination, that means naturally the next question, once I have linear combination, my next question, oh, so these solutions are, they are in linear combination. What's about the dependent or independent? Whether they are linearly dependent or linearly independent. That one has to make sure, right? So linearly dependent and linearly independent solution, exactly same thing, the definitions I gave it to you in your chapter 4.
But just keep in mind this thing that I'm talking about the matrix. Let x1, x2, xk be a set of solution vectors. See, set of solution vectors, x1, x2, x3, they are the set of solution vectors. Get over here. These are the vectors. Set of solution vectors for the homogeneous system x dot equal to ax on the interval I. Then we say that the system or the solution x1 to xn is linearly dependent if there exists constant c1 to ck, not all zeros. Exactly same definition with the things in mind. They are not just variable, they are the vectors, right? Column vectors, I would say. So not all zeros, such that c1 x1, the linear combination is equal to 0. So once you write your linear combination, make sure that at least one of these c1, c2, c3, out of this c1, c2, c3, ck, at least one of them should be different from 0. Should be different from 0. And they are linearly independent if all the constants are 0 at the same time. That means this your vector, if you are extending your vector, that means it is linearly dependent geometrically. And if your vectors, one vector is moving like this, second vector is moving like this, if there is no relation between two vectors, that means it is called linearly independent. And these are the solutions of the given matrix. And that is a definition goes exactly parallel to chapter 4, keeping in mind this thing that we are not working just with x1, x2 as a variable, but we are working with x1, x2, xn as or xk as a column vectors. Okay, x11, x12, x13, number of columns, number of vectors are there, number of variables are there in your one column vector. So please keep in mind this thing. Okay, and now the main thing is homogeneous linear system. Homogeneous linear system, just 1 minute guys. Homogeneous linear system, that is article 8.2. 8.1 is over. 8.1 is over.